So today we're going to have two presentations. First is going to be presented by me, and the second one will be presented by Andreas. So the two young researchers that are included in Spatra project.
So first of all, thank you everyone for participating in our presentation. Our motivation for our work comes from Spatra project. Spatra includes drones, includes some IoT from our side, some machine learning. Our DUS principal investigator is Mr. Professor Antonios Kasteratos. Our deputy principal investigator is Assistant Professor Lucas Bambis, and me, I'm the leader of research, Andreas. We have we have a roadmap. First of all, for our presentation. First of all, we have the drone section. Drone section include the drones, of course, everything we have to know about the drones. We have to know about the components that the drones have and are attached to it. And last, we have some features like the GPS and the location and the coordinates of the drone. In the next section, we will talk about the IoT. IoT refers to Internet of Things. Internet of Things refers to something connectivity, let's say about the drone and the Wi-Fi or some sensors. And here you can see a use case that we have in a highway that we monitor the traffic flow. But we will use the drone instead of these sensors. In the next section, we have the machine learning. Machine learning, as you can see here, we have some multiple objects detected. We will use the machine learning to detect tracks, to predict the traffic flow and the congestion near borders or highways, and the parking occupants. And the last section we are going to discuss is about the combination of those sections, which is drones and IoT and logistics. We have the data analysis. We have here a use case, an image from the borders. We have congestion and traffic flow here to estimate. And last, we have the IoT and logistics. So let's get started with what is a drone. First of all, we all know that drone, one of the most unique drones and most known is the Phantom 4 drone here, is the DJI Phantom 4. Some basics about drones is that it belongs to UAV category. It means that it can fly without a pilot, autonomously or with a remote controller. We have some basic parts like the ESC, which is electronic speed controller. We have the flight controller, which is the main core of the drone. We can program it. We can set it to go to specific coordinates. We can additionally do some machine learning to it. We also have the motors, of course, the battery and the propellers that are mounted to motors. And here we see some DIY. This is from a research lab. And they made the DIY drone, which includes the NVIDIA Jetson, which is a platform that can be programmed and used as a flight controller. We have the Arduino Nano because it can control the packaging delivering system. This drone can fly to a specific destination and leave a package and then return to its home position. We see also a GPS. This is an antenna. A step down, this is for the electronics and the motors, and some servo for the delivery, for the package. So where do you use? Drones are being using a lot, as we all know, in the agriculture. We can spread some seeds, we can water the plants, we can also map the area with a 3D model. We can also extract some information about the grass, the field, like if it is yellow, the grass, it is dehydrated. We can also do some transportation and delivery systems. We also can use them as an ambulance. The drone is faster than an ambulance. And this is very important because it will be in near future that the drone can monitor, can delivery some pills or some drugs to someone who needs, or maybe it will give you a CPR. And we have also the construction. Construction means we can monitor bridges, we can make and extract 3D models from buildings, or we can extract some information about the infrastructure like the highways or the roads. And last, we have the entertainment. As you can see here, we have multiple drones that are connected to each other. Each drone has its unique ID. It takes a light, as you can see here, and you can make some waves or even shapes like dragons, and you can make shows looks very nice. So let's start with the basic idea of what is Internet of Things. Actually, I don't want to explain what is this, and I will say what is this image. As you can see here, we have multiple sensors that are connected to something like Internet. So if you have Internet sensors that are being connected to Internet, and those sensors can send you data from a field, so this is called IoT. Basically, IoT refers to something that connects sensors to Internet or some other protocols like Zigbee, LoRa, or you can use 5G satellites, and those data are being stored to a cloud, and this cloud it goes to the end user. How it works? We have 5 steps for the IoT. First of all, we have the data ingestion. You take all the data and you collect from sensors. Then you transmit the data through some middleware, we say it. Middleware refers to NB-IoT, Zigbee, those are protocols, MQTT. We transmit it and we data processing this. How do we do it? With some machine learning algorithms, with some computer vision. This is the AI in general. And one step before last is the data visualization. Here we do some graphs. We can say that you can get emails from alerts that the field, for example, a farmer needs to plant needs to water the plants or needs to go there that something goes wrong. And then we do some data analysis predictions. We take all this data, we store them, and from the history we can predict future patterns that might come across. The Internet of Things has 5 steps. We can analyze them by, first of all, the physical layer. We have the sensors like here, the gas. This is Arduino sensors are being used in basic student platforms. And this is a gas sensor, this is a microphone, ultrasonic. You take those sensors, the data are being transmitted to a network layer and then to a middleware. So the network layer only do the job to take the data and upload them to Internet. The middleware layer has the servers, the API, the cloud services, and this is the data where it's being stored. And the application layer, as we saw here, is the visualization part and the machine learning. And the business layer, it's graphs for businesses, graphs, drawings, predictions for future. In the next section, we're going to discuss about the machine learning. Machine learning actually and computer vision refers to AI, but actually it's not AI, it's a subset of AI. As you can see here in the image, we can see some patterns from those tracks. Actually, they are all the same shape. They have the color is white in the top, and actually we can see here an example of the tracked images from a robust algorithms. This is one of the most known algorithms nowadays. It's YOLO V11. It's the latest version and currently has the best performance to compared to all the others. We additionally have the object detection. Object detection is a technique that do a classification and localization. So localization is what is this? This is a track, and where it is in the middle of the frame. The images and tracks are always automatically tracked and detected if we train the model. And such system can analyze some patterns or behaviors for the road and the highways and the parkings, as we can see. I'm sorry. Yeah. So in the last section, we are going to discuss a little more further about what we saw so far. Spatra, it's one of the most important, I think, Horizon project nowadays. Actually, it's a EU-founded project. We use satellite technology like Galileo Copernicus to improve the transportation system. We integrate some satellite, drone, and ground to address some challenges like congestion, parking occupancy, and traffic for optimizing the traffic management. And the project, of course, involves a consortium of technology experts and aims to optimize logistics and change infrastructure monitoring across Europe, specifically for vehicles like trucks. We came across with three solutions about this issue. First of all, it's the IoT for real-time traffic data. Drone, we collect some data and we refer to images and videos from highways near borders with high congestion or traffic flow, we can say, and travel times, providing a real-time insight for logistics operators. So we can avoid the traffic jams. And we have the drone monitoring for traffic and parking. Drone will fly above parking areas. We can collect aerial images. With the help of a machine learning model like we saw in the YOLO V11, it can predict the parking occupancy and the estimate time of arrival near borders. And last, we have the predictive traffic management. We use all the data collected from the last two tasks, and we can use some AI algorithms to predict some future traffic congestion that are going to be, enabling logistic companies to plan deliveries during off-peak hours and avoid congestion, of course. So let's see each one. First of all, we have the IoT for real-time traffic data. Using state-of-the-art machine learning algorithms, vehicle waiting in the queues near the borders can be detected by drone. The next step is to track them as needed, and finally calculate their speed. To find the current coordinates of the image where the track was taken, the OceanMA authentication protocol is used. This protocol established a secure connection to avoid spoofing attacks. Finally, by knowing the queue length and the vehicle's current position, the estimated time of arrival at the borders can be calculated. As you can see here in the image, the drone is in the highway and can detect trucks that are going to a destination. And in the next solution, drone monitoring for traffic and parking, using a machine vision and deep learning technique. The system is able to detect available parking spaces and distinguish them from occupied one. The images are geotagged, of course, as we said before, using the OSNMA protocol, and then are stored on a local device or on a ground station, and subsequently routed through an IoT-enabled API to a central server. And finally, this data is evaluated and analyzed to optimize the logistic management. And you can see here the drone is flying above the tracks, and it can see here the parking space it is available, and this is the occupied. And it can do it for multiple vehicles, multiple trucks, and it can make an output like the whole parking space available are, for example, 20, and the occupied are 30. And last one is the predictive traffic management. By analyzing all the data from available parking spaces and border traffic flow, we can make a predictive models to identify the recurrent patterns over time. These patterns allow us to optimize the traffic management and logistics for the congestion and the parking occupancy. And by recognizing all the trends, such as peak traffic times or frequent parking spaces shortages, authorities can take proactive measures. And ultimately, this predictive capability, it enables for the end user a better route planning, improve resource allocation, and enhancing the overall transportation efficiency. Thank you. If you have any questions, please let me know.
Okay, if there are no questions, I will start sharing my screen to start again with my presentation. Okay, can you see my screen?
Yes, yes.
Okay, thank you. So as we said before, in this presentation, I'm going to present how we can use the potential of Sentinel-2 data for logistic planning. So what motivated us to actually start this research about Sentinel-2 data is, first of all, Serbia's geostrategic position, as it is positioned in the central of Balkan, and it connects Western Europe with Asia. Also, Serbia is not a member of European Union, so moving between Serbia and EU countries is not that easy, as there are border controls. And also for Batroci border crossing, which is a border between Serbia and Croatia, we know that at the peak of the season, the truck queue lengths can go up to 20 kilometers. So those three things united motivated us to start doing this research. Also, when we are talking about logistics plannings, those are the data that were used in previous research. So we can see that here we have either pretty expensive data sources in terms of money, in terms of infrastructure, but also we have Twitter data, which we cannot rely on because of its granularity. So that's why we decided to, let's say, find the middle solution of the data source and to try and see what happens with it. So as I said, we're going to use the Sentinel-2 data. So I'm going to explain some, let's say, properties about this data. So when it comes to this data, we have 13 bands. During our research, we tried with many bands, but we decided that the band that has the smallest possible resolution is the best one for us to detect some kind of movements. So the best resolution is 10 meters, but it can go up to 60 meters. So in this research, we used only 3 channels, R, G, and B. So the visible spectra that has a resolution of 10 meters. A very important thing for the Sentinel-2 data is its sampling period. So we have 2 satellites. Each of them has a 10-day sampling period. So when we combine those data, we have a period of 5 days. And as I said before, it is suitable just for detecting vehicles that have a length that is larger than the smallest resolution we have with Sentinel-2 data, which is, let's say, trucks or buses. So we're not able yet to detect, for example, cars because they have a length less than 10 meters. And we developed 2 algorithms here. First one is used for detection of moving trucks on roads leading to border crossing. So in order to, let's say, extract the density of the transportation. And the second algorithm is devoted to truck queue length at border crossing when it comes to only trucks. So the first algorithm consisted of several phases. First is the phenomena we used for this detection. So we use a visible spectra R, G, and B of Sentinel-2 images. And what is really nice when it comes to the combination of these 3 bands is that moving vehicles that have length longer than 10 meters can be visible as a rainbow because we have 3 bands. Formally, they are, let's say, recording, taking an image at the same time, but practically it's not at the same time. So because of that, when we combine them, we have something like a rainbow, and that's how we detect trucks and other long vehicles. Also, what we use is the OpenStreetMap data in order to detect the highway, the road that we're interested in. And then what our algorithm did is that after we detected the road, we applied the algorithm, which is based on the rainbow, on the phenomena we previously mentioned, in order to detect the moving cars. So you can see here the metrics of our algorithm. So it's not that bad, but what did not work for us is that we could not we could not divide of our detection what is bus, what are buses, what are trucks. So that's why we decided to not use this approach, but to use another approach which was based on detection of the queue length at border crossing. So as we previously said, the resolution of the Sentinel-2 images is one of our biggest problems. So 1 pixel stands for 10 meters. So that's why we wanted to try to enhance the resolution, and we enhanced it using a deep neural network. So the resolution after using this a deep learning network is enhanced 10 times. You can see the results of this algorithm, of this neural network in the image on the right. So after we did the enhancement of resolution, we have steps which are listed below. Those steps were, let's say, primarily focused on adaptive processing of the image. And then after following all these steps, we could detect the line at the border crossing. So here is an example. So we have an image, and then on the right side we have a detected detected Q. So what motivated us most is to make an adaptive algorithm, as you can see on the right side. So there are some clouds. We wanted to make our algorithm to do great in different scenarios that are all happening in one image. As you can see, if we only take a look at the first half of the image, we could not predict that there will be clouds on the second part of the image. So we tried to make an algorithm that will be adaptive in different unpredictable scenarios. And the metrics regarding this algorithm, as you can see, are better than the previous one. So the Q is detected well. And also, what is our future work is because our problem is that Sentinel-2 provides data images every 5 days. So that is the best case scenario. Sometimes it's 10 or 15 days due to different weather conditions. We can use this data only in form of already trained models. So we have the models that are trained on this data, and we can use the output of these models. For example, based on previous two algorithms I mentioned, we could have a model that will estimate border Q length, or we can have a model that will estimate the transport density. But yet we're not able to use this data in real time just through trained models. So thank you for your attention. Do you have any questions? Okay, so I guess that's it for today's webinar. So thank you everyone for joining us. Thank you, Andreas, for your presentation, and have a great day. Thank you.